Okay, good morning. This is a video about basic logarithmic properties. And so this is where we're going to learn what a logarithm is. And so here's a statement that is very, very helpful, and it's also true when you're dealing with logarithms. And the statement is that a logarithm is an exponent. If we keep that in mind, it turns out to be very handy as we deal with logarithms. But first, let's define it as a function. It's a function. We've already seen the graph. Let me just remind you what the graph looks like. This is the basic graph of a logarithmic function where the base a, and so the base here, f of x is equal to log base a of x. This is what the function looks like, is greater than 1. So if the base is greater than 1, it has this vertical asymptote, x is 0, has this x-intercept at 1, and it is an increasing function. The domain of this guy, the domain, is from 0 to infinity. So you can only put positive numbers into this function. So when we define this function, f of x is equal to log base a of x. The base a, here's a couple of distinctions. A does not equal to 1 because, and also a is positive. These are the distinctions that we make right there. Okay, so this is the logarithmic function, and this is the statement. A logarithm is an exponent. Now, this is an equation in logarithmic form. Sometimes we write f of x, sometimes we write y equals. So I'm going to write this as equals to y. Log base a of x equals to y, which is the same exact thing as y, or f of x, equals to log base a of x. I'm going to write it this way because there's another statement we make a lot of times. Let's say log base a of x is equal to y if I double f means if and only if this other statement I'm about to write is true, and this is the exponential form. A raised to the y equals to x. Okay, this is called the logarithmic form of a function, and this is the exponential form. And we can convert back and forth. These are both equivalent statements. They're both true. It says that log base a of x is equal to y if and only if this other statement is true. The base a raised to the power y is equal to x. So let me put numbers in here, and this would help us see it just a little more clearly. And then I'm going to repeat this phrase, and we're going to see how this might make some sense to us. Okay, if we've got, this is a true statement. If I say log base 2 of 8 is equal to 3. This is a true statement. Log base 2 of 8 equals to 3. I'm going to write it in its exponential form. The exponential form is a. If you look here, here's the base a, here's the base a. In this case, it's 2. This is true if and only if 2, the base, raised to what's on this side, the y, raised to the power y. In this case, the y is 3. 2 raised to the third power is equal to what's x, which is called the argument of the logarithm, is equal to 8. And we see this is a true statement. 2 to the third power equals to 8. Sometimes I write this down just to help me find my way through this. So let's read this again. A logarithm is an exponent. A logarithm equals to an exponent. Do you see where the y ended up? It ended up in the exponent. This logarithm is equal to an exponent. Do you see where the 3 ended up? It ended up in the exponent when I wrote it in exponential form. So this is exponential form, and this is logarithmic form. Okay. Now, here are two little statements I need to make about logs. The base a, there are a couple of kind of special bases. The base a, if we have log base 10 of x, when the base is 10, how we generally write this is without writing the number 10. We write log x. These mean the same thing. So if you see the log of something and they do not write the little base, the little subscript there, it is understood to be base 10, and this is known as the common logarithm. if they write this. If you see this log base e of x, when the base is e, we generally write this like this, the ln of x, or sometimes they might write it as the ln of x. When you see just the ln of x, this right here is understood to be log base e of x. When they write ln instead of a log base something, it's understood to be base e. This is called the natural logarithm. Now, on your calculator, you will see log. You'll see a button, log. And on your calculator, you will see a button, ln. Those are on the face of any scientific calculator. So if you look at what they're next to, if you look at the second function, if you find the log button, if you look in blue above it, it is 10 to the x is what you'll see. 10 to the x above this. 10 to the x. And if you look above the ln, e to the x is what is above that. So that's not coincidental. That's because ln means base e. And that's because log means base 10. Okay, now let's look at the worksheet that we have. We just have a few problems that we're going to be dealing with. A lot of this is handwritten, so you'll see the statement there, log base a of x is equal to y, if and only if a to the y is x. That's what we had here. The first few things we're going to do is change from exponential to logarithmic form. From exponential to logarithmic form. So it goes like this. If they say change from exponential to logarithmic, and so since you have it on a worksheet, I'm just going to abbreviate here. Right here we're going to be going from exponential to logarithmic form. Okay, the first one that we have on the sheet is, let's see, a is 1.2 to the third equals to m. This is exponential form. The second one is e to the b is 9, okay, and then we have, was that all we had? Just b, oh, and then we had, see, a to the 4, see, a to the 4 is 24. Okay, so here is the deal. When you're going from exponential to logarithmic form, a good start is to write down the word log, okay, so we say log. Log. Now, it's always log base something, log base something. Now, the base that we write here is the same base that we see being raised to a power. For instance, if I have 2 to the third power, 2 is the base, 3 is the exponent. 2 is the base, and 3 is the exponent. For instance, so over here in this exponential expression, 1.2 is the base, and 3 is the exponent in this situation. So when I'm converting to log form, it's always this log base. The base here is the same base as it was in exponential form. Log base 1.2 is equal to, if you remember the phrase, a logarithm equals an exponent. A logarithm is an exponent. What's the exponent here? 3. A logarithm is equal to exponent. And so this m becomes the argument. This is how we convert to log form. Log base 1.2 of m is equal to 3. Let's do b. This reads e raised to the b power is 9. So you write down log. What is the base? The base is e. A logarithm equals to an exponent. The exponent is b. And the argument is 9. This is true, but this is a more commonly way to write it. The ln of 9 is equal to b, because we know log base e is written ln, natural logarithm. Okay, let's do this one. Log, what's the base? Well, the base is the same base here, a, log base a. You remember that a logarithm equals to an exponent. What's the exponent? 4. And then the argument becomes 24. And that's how we can change from exponential to log form. All right, you have another set of problems right here. Let's change from log to exponent, from logarithmic to exponential form. So let's do that. If we have to change from log to exponential form. Here are a few problems we can do. A says log base A of 4 equals to 5. We have log base E. Log base E of B is -3, and we have log base 3 of 5 is C. All right, so I just gave us 3. Okay, for changing from log to exponential form, the word log won't be in there anymore. It's just going to be a base to a power equals a number. All right. What is the base? Well, it's always the same base. It's log base A, so the base that's being raised to an exponent is A. A logarithm equals to an exponent, so a logarithm equals to 5. This is the exponent. A to the 5 is equal to the argument 4. Right here, what is the base? The base is E. So they could have written it like this, or they could have written it like this. The natural log of B is -3. Even if they gave it to you in this form, you would understand that the base is E. This logarithm is equal to the power -3, the exponent -3. E to the -3 is equal to B. Right here, what is the base being raised to a power? 3. Is being raised to the power C. And this is equal to 5. This is converting from logarithmic form to exponential form. Okay, the next thing we have is to evaluate the logarithmic expressions. Number, I don't know, my worksheet's kind of messed up. Evaluate the logarithmic expression log base 2 of 16. So let's see what this equals to. Log base 2 of 16. What are we going to do here? All right. Make a little more room. Log base 2 of 16 goes like this. Log base 2 of 16. And then they want us also to evaluate log base 3. Log base 3 of 1 over 27. And then they want just these two. Okay. So, let's do this. Let me write this beside log base 3 of 1 over 27. Okay, let's evaluate. Sometimes what I find very helpful to do, and so this might be like without a calculator. I think without a calculator we can do these. Without a calc. Okay. What I find helpful is to say this is equal to y. Okay, I'm going to say this logarithm is equal to y. Set it equal like a function. Okay, then you would say, if you convert this to exponential form, it helps quite a bit. So how would we convert to exponential? We'd say the base, which is the base 2, raised to the exponent, which is whatever the logarithm is equal to. 2 to the y is equal to 16. So then you would say, well, 2 to what power equals to 16? And so you could start saying 2 times 2 is 4 times 2 is 8 times 2 would give you 16. And pretty soon you'd realize that 2 to the 4th would give you 16. And so y has got to equal to 4. That is, sometimes they'll ask you to solve without a calculator, and you can do it by converting to exponential form. Let's convert this one to exponential form. What is the base? It is 3. What is the exponent? It's whatever the logarithm equals to, because a logarithm is an exponent. A logarithm equals an exponent. 3 to the y is equal to 1 over 27. Now this one we have to think about a little bit. In 27 I can see some 3's. Let's just think about 27. 27 is 3 times 3 is 9, times another 3, oops, that's 3, times another 3 would be 27. So 27 is equal to 3 to the 3rd power. But the situation is, it's in the denominator. So right now we have 3 to the y is 1 over 3 to the 3. I need this side of the equation to look like this side of the equation. So if we remember basic exponent rules, we can raise the power up, raise the exponential form up. And so we get 3 to the y is equal to 3 to the -3. At this point, we can set the powers equal to each other. Y is -3 because the bases are the same. and we were able to evaluate that logarithm right there. This logarithmic expression is equal to 4. This logarithmic expression is equal to -3. All right, now we're going to get our calculator out and just practice pressing buttons. And so let's do that. What if they say evaluate to the nearest hundredths? Let's evaluate to the nearest hundredths place. So let's see here. What if we've got this? It says evaluate to the using a calculator, and so evaluate with a calculator to the nearest hundredths. All right, so the first one we have is the natural log of 5 divided by 3. The second one we have is the natural log of 2/3 divided by negative, I can't read my writing, I'm going to say negative 3.1. And then the third one we have, is that 3 times the log of 7 minus 2. All right, we're going to evaluate these with our calculator. So get your calculator. And so these are the buttons we're going to be pressing. ln, we know that means natural log, log base e. We have a button on our calculator to use that. So what I'm going to do is press ln, and what automatically comes up is a parentheses, and then I'm going to enter 5, my argument, and close the parentheses and say divided by 3, and hit enter, and I get 0.536. This is about equal to 0.536. If I'm going to the hundredths place, that's this place. So I look to the right, there's a big 6. So this is going to be 0.54 is going to be my answer right there. Okay, for B, in your calculator, say the natural log, parentheses, the parentheses automatically comes up, and say 2 divided by 3, close parentheses, and you're going to divide that by negative 3.1, and I get 0.1307. So to the hundredths place is here, right? So to round that to the hundredths place, this is going to be 0.13 is going to be there. If you notice, I put 0.13 here and I put 0.54 here. Those mean the same thing. If you don't see anything in front of the decimal, there's a 0 there. Okay, let's do this one. The answer to this one is 3. We're going to say 3, and this time don't hit the LN button, hit the LOG button, and we understand this to be base 10 because we don't see anything written. LOG, and the parentheses of 7, and then close parentheses. So right here, this is the important moment. This is the argument of the logarithm. So you need to enter it 3 log parentheses 7. You close your parentheses, and then you say minus 2. And then this is equal to 0.535. So if we want it to the hundredths place, we're going to round to here. And so this is going to be 0.54. Okay? So whatever's right next to the logarithm is the argument. And if there's other things added or subtracted, that's separate. Okay, great. So now let's find the domain of the given logarithmic expressions. So let's do that part. Find the domain of the given log expressions. All right, find the domain. Okay, so if you recall, at the very beginning, we kind of looked at the curve of a logarithm, okay? And so even if this logarithm had a base that was between 0 and 1, it would look like this, okay? But in either case, the domain are values that are positive. In either case, whether the base is bigger than 1 or whether the base is between 0 and 1, the domain has to be positive. So, with that in mind, with knowing that the domain has to be positive, this is what we'll do. We'll find the domain for this function, g of x, which is equal to the natural log of x minus 1. And then we'll find it for the natural log of, no, sorry, 3 minus 2 times log base 4 of x minus 2 minus 5. Okay, and then C, we want to find it for g of x. Let me give this guy h of x. Let's give him a name. Was it f of x? Okay. And then the last one, g of x is equal to the natural log 1 over x minus 5. Okay. Here's the deal. Whatever you're taking the log of has to be positive. So you take whatever you're taking the log of, x minus 1, and you say you have to be positive. You have to be greater than 0. Then you just solve for x. Add 1 to both sides. X has to be greater than 1. In interval notation, it would be from 1 to infinity. This is the domain of that logarithmic expression. Right here, this is not in the log expression. This is not in the log expression. This is in the log expression. Just take this part, x minus 2, x over 2 minus 5, and say you got to be bigger than 0. Solve for x. Add 5. Multiply both sides by 2 to kill your fraction, and you get that x has got to be greater than 10. And so when you write that, the domain here would be from parentheses 10 to infinity. This one, g of x is the natural log of 1 over the x minus 5. I'm going to rewrite it over here. Okay, whatever I'm taking the logarithm of has to stay positive. So, 1 over x minus 5 has to stay positive. This is a division problem. Every fraction is a division problem. If you divide a negative by a negative, you get a positive. If you divide a positive by a positive, you get a positive. So since the numerator came to us as a positive, we would have to say x minus 5, the denominator, you also have to stay positive. So x minus 5 has to stay positive. We'll add 5 to both sides. And so the domain here is going to be from 5 to infinity. Now let's just mess with this for just a second. What if? What if? This was not a 1, but this was a negative 1. What would be the domain of this problem? Well, this is a division problem, and a negative divided by a negative would produce a positive. So in that case, we would take the denominator and we would say, okay, when are you negative? And as long as you're negative, a negative over a negative gives us a positive, we would solve this and we get x is less than 5. So from negative infinity to 5 would be the domain if we had that a negative right there. Okay, the very last thing on this worksheet is I'm using the change of base formula. So most calculators these days, fancy calculators for sure, have every base that you want to put in. However, what is really important is not that we can press all the buttons on our calculator, but that we understand the algebra. So I'm going to practice us learning algebra. And so when I give you guys a work to do, if we have to solve an equation, let's say, I'm going to have you solve it. I'm limiting the bases you're allowed to use to base E and base 10 because that's going to make us make sure we know how to do the algebra that's involved in logarithms. And that's what's important moving forward to your next course. So right here, let us practice this change of base, and let me tell you what this means. If you've got log base b of m, you can rewrite this statement into a fraction, log base c, and the c stands for the base of your choice. The choices that I'm allowing you to use are base e and base 10, what you would find on the face of any scientific calculator. So log base b of m is equal to the log base of my choice of m, the argument, divided by log base c of my choice of b, the base. And so it goes like this. If we have to evaluate 1, 2, and 3 using the change of base formula, log base 12 of 4, log base 6 of 17, log base 18 of 54, I'm going to rewrite this. Because I've got a teacher who's not going to let me use all the buttons on my calculator, I have to use this formula. So what am I allowed to use? Base E or base 10? So goes like this. This is log base b of m. So this is equal to the log base c of my choice. I'm choosing this 10 this time of 4, the argument, over log base 10, that's c, I chose c to be 10 this time, of 12. Now, I don't have to write this when it's base 10, right? So I'll put this in my calculator. So in your calculator, say, okay, log, L-O-G, of 4, close parentheses, divided by, press the log button, enter 12, close parentheses, and you get 0.5578. 0.5578. So if we go to 3 places, let's go to 3 places. Let's round to here. This is about 0.558 is what that would be. Now, what if you didn't choose log base 10, but you said this is equal to the natural log of 4 over the natural log of 12? You can put that in your calculator, and you will also get exactly 0.558. So for 2, this is the choice. I'm going to choose base e for number 2. I'm going to say this is equal to log base e of 17, or ln of 17, over log base e of 6. Log base e of 6. And so this gives me the natural log of 17 divided by the natural log of 6 gives me 1.581 to 1.5812. So this is 1.581. If you were to use log base 10 over log base 10, it'd be the same. Let's do log base 10 here. This is equal to log base 10 of 54 divided by log base 10 of 18. And so that gives me log base 10 of 54 divided by log base 10 of 18 gives me 1.38009. 1.38009. If I'm rounding to the third, I get 1.380 would be my answer right there. All right, this is basic log properties.